Now the last thing we got to set up is the interrupts, the interrupt register. So timer counter interrupt mask register, and these are the 3 bits that are affected. When on reset there's 0, so it means none of these interrupts are enabled, and I want to set this one here, output compare interrupt enable A, and that's the bit 1. So let's go back to our code. What was the name of that? TMSK0. TMSK0. Oh, TIM. There we go. Equals, and I'll just do it again, 0B, and 1, 2, 3, 4, 5, 6, 1, 0. So now I've enabled the interrupt. So that's how to set up the timer counter to do what we're doing here. I encourage you to, on your own time, if you want to learn how to do this, get the data sheet. You can get it from Atmel. It's a free download, and read through it. So now I'm going to create an interrupt service routine in order to do something with this timer counter when it interrupts. And I'll show you how interrupt service routines are written. They're not defined in quite the same manner as that, as a regular function. They still are functions, but they're a special function. And so I'm going to show you how to do that. And I'm going to show you something else here. If we go to the help, now you have to add content to your help. Well, when you first set up Atmel Studio, there's no help, and so you can click on this one here, add and remove help content, and it brings up another window and shows you what you've got installed already, and what and this here shows you what you can get. So there's quite a lot of help information that's available here. I just want to get rid of that so we can actually see. Oh, is that really useful? No, it's not really very useful. So you can look through this and decide what you want. And there's a lot of stuff here, and you don't need most of this. You're not going to need, especially with what we're doing here. What you're going to need is this one. Where did I? 80 mega. I already got it installed. It's not that one. AVR. Here we go. Can't remember where it was. Oh, here it is. This is it. So under users guides, look down here, software, and we're looking for AVR Lib C. So I've already put it in here and installed it. So you need to do that. It'll go to the internet. It will go to Atmel's website, and it'll download it and put it in for you. You don't have to do anything else. It's quite nice how it works. And that's all you're going to need for what we're doing here. So let's look it up. Oops. Let's view the help. And AVR Lib C, and we're looking for library reference, and there's going to be all kinds of stuff here. And so what we're looking for is interrupt.h. And we're looking for the names of the interrupt vectors. There we go. So the way you produce or create an interrupt vector is simply doing this: ISR followed by, in brackets, the name of the interrupt vector, and then the normal curly brackets that a function would use, and then you write your code. And you can read through this on your own. I'm just going to show you how to know which interrupt vector there is. Now, I briefly passed over the vector table when we looked at the listing of the output listing of the compiler. And there's, I believe, in the ATmega 328, there's over 20 different interrupt sources, and each one has its own vector. And so we have to find the one we're interested in. So it's all alphabetical here. This is the this is the name that we're looking for. This is an old name for an older version of the AVR libc, and we're looking for the name under this one, and it's all in alphabetical order, so we'll just go down to T for timers. So we're looking at timer 0 compare a vector, and that is incorrect. So we're looking over to see what microcontrollers it works with. None of these are the ones we want, so we look down a bit more. Here we go. This is what we're after here. This is the one we want. Timer 0 compare A, and it should have ATmega 328. Actually it doesn't. Believe me, it works. This is the correct one for it. I'm not sure why it doesn't show up in this list. It has everything else. I mean, it's got the 168, so it should be the same for the 328. The only difference between a 168 and a 328 is just the amount of memory. The 328 has twice as much RAM and twice as much flash inside it as the 168. But anyways, this is the vector that we're looking for. So let's create our interrupt service routine. So ISR bracket TIMER, and there you go. The virtual assistant came up with the name that I wanted. Type it in there and put in our curly brackets, and there's what we're going to do in our interrupt service routine. Now I'm just going to do something really simple here, and this is how you should do interrupt service routines. Interrupt service routines have to be as short as you can possibly make them, because you remember, when the interrupt is being serviced, the microcontroller is not doing anything else. It's only doing one thing at a time, and it's doing your interrupt service routine. So you try not to do very much in an interrupt service routine for a couple of reasons. Why? It takes away the processor from other processes that might need it, but it also what was the other reason? It just popped out of my head. I'll get back to it. I'll probably remember. So we're going to make this one super simple, and all I'm going to do here is set a flag, and then we're going to look down here between our states and looking for that flag. So I'm going to create another variable up here, an 8-bit as well, and we'll call it 10 millisecond flag. And a flag will be true, or let's see, a flag will be false if it's 0, and it'll be true if there's anything else in there but 0. So what we're going to do here is we'll just, oh, actually 10 millisecond flag isn't going to work, because we're not allowed to start a label with a number. You have to start it with a letter. So let's go T0. That works. Now you can see how it changed color. It was black before I put T0 in there. So let's go T0 10 millisecond. Oops, T0 10 millisecond flags equals 1. So every time the 10 millisecond timeout occurs, we'll set that flag. That's all we need to do in the interrupt service routine. Very simple. Now, what we're going to do here in our while loop, because we're not doing anything else, we are simply going to look at that bit or that flag and wait for it to be set. So we will put the whole switch statement inside an if statement. So we'll start with the if statement. So if T0 1 millisecond flag equals 1, and then we'll do stuff. Now the first thing you need to do when the flag is set, so you got to clear it, because you don't want to forget that. So T0, make it equal to 0. Now let's just put our curly brackets down here at the end. We're going to have to do an indent as well. So now the switch statement gets indented to match up with the if statement. Now you might think I'm being a bit anal about how I write my code like this, but it's important. that you do it this way. It just makes the code so much easier. It's called, the term is called, it's an old term, it's been around for a long time, it's called pretty printing. But it relies on white space to separate your parts of the code to make it a lot easier to read and understand. And so every time you've got a set of curly brackets, you indent everything inside the curly brackets. So in keeping with my method of keeping track of stuff, I'm going to copy this, and at the end of the if statement, which is here, I'm going to put another comment, and so I know that's the end of the if statement. And actually I want to keep going here. Let's make this one, we know this is the end of the while statement, so end while 1. Oops. And if you want to be really complete, this is end main. So now what we've done here is when this flag gets set every 10 milliseconds, we just simply clear and we go do something else. Now we're not going to run into this state thing here because state doesn't change. So we're going to have to change state. We've got to increment LED state. So I will do it inside another if statement, and we're going to increment. So this double increment or double plus LED state, so it means increment LED state by 1 and test. So is it equal to what was our max LED state? So this is why I presented that in that enum statement up in the top of the code here, that extra state, the max LED state. And we'll put in curly brackets here. And what we're going to do is LED state has gone past the end of LED state. If it's gone past the end of LED state or the end of the last enum statement, we'll just make LED state equal to LED state 0. Starts all over again. And that's all we need to do. Leave a bit of space here. And that's it for our program. Oh, actually, not quite yet. One thing I forgot to do. We're not going to run this every 10 milliseconds. We have to create a counter to count our 10 milliseconds. So we'll do that next. So let's create another variable here. And let's call it our, what should we call it here? We're going to count our 500 millisecond timeout. Let's have let's call it LED delay, and we're going to initialize it this time. Now it's going to count the number of 10 millisecond interrupts to give us 500 milliseconds, for example. So we'll make it 50. Now here's a problem that I have. I've now created what I call a magic number. It's just a number that sits here and it doesn't mean anything. It doesn't, like, you read the code and you go, well, what's 50? You have to kind of think about it. So let's give it a name. Let's call it LED time out. Or actually, let's call it, give it another name, blink time. LED blink time. So up here I'm going to make a define statement, LED blink time, because we're going to use this more than one. In fact, I can put it here because we're not using blink delay anymore. So LED blink time becomes 50. Now the reason why I did this is, first of all, it makes the code more readable. This actually means something. And then it gives me one place in the code with which to look for to change. If I wanted to change this value, if I say wanted to have it 250 milliseconds, I can come to this place here and it will be and I can just change it here to 25. It's going to show up here and then it's going to show up down here. So if 10 millisecond flag equals 1, so the 10 milliseconds has occurred, but we're not going to increment our LED state here yet. We're going to actually increment. So we'll do it again with an if, because we have to watch for the overflow. So what do we call it here? LED delay. So again, we're going to increment it. Actually, no, we're not. We're going to decrement it, but we're going to do it a little differently. LED delay. We're going to decrement it post decrement. So, oops. Well, let me finish typing this, and then I'll explain what I've done here. So what this statement does here is first of all, it checks LED delay to see if it's equal to 0. If it is equal to 0, then we're going to do something here. If it's not equal to 0, it's going to be greater than 0, because we're starting it off at 50. So if it's not equal to 0, then it will decrement it. So when it does reach 0, we want to make it back up to 50. So we're going to go LED delay, which is that, equals LED blink time. So this is why I created that define statement up at the beginning of the code, is because I'm going to use this LED blink time in more than one place in the code, and it makes it easier for me to update the code. If your projects get bigger and bigger and more complicated, you might have this stuff, something like this, buried deep in your code, and then you realize, oh, I want to change the blink time. I'm going to have to go to every place in the code where this is being used, and if you're looking for the number 50, it doesn't mean anything to you, and you got to dig through the code and actually understand what it's doing, and then go and change that value. Think about it if you go back to your code 6 months or a year later and you want to modify it, and you've forgotten how it actually works. You're going to waste a bunch of time trying to figure out how it actually works, to figure out what magic numbers you actually have to change. And so that's why I did it this way, with a define statement, a constant here. Now, let's see. What we're going to do is we have to it's kind of wrong here. This is only going to get decremented if, okay, no, hang on. I'm writing this on the fly. I haven't put any thought into how to do this, so I'm writing it as we're going here. So please excuse my hesitation here as I try to figure out what I'm trying to do here. So I've got to figure out the order here. If 10 millisecond flag is set, it means our 10 milliseconds is elapsed. We need to clear that flag, and then we count the LED delay. Okay, if the LED delay does indeed reach 0, then we got to do something. So we've got to change the LED state to here. And so we'll change the LED state, and then all of this switch stuff, we don't need to run this every single time. We don't have to, and so we can put it in here. So if the 10 millisecond flag, or if the delay has reached our 500 milliseconds or whatever it is, which will be here, then we can execute all of this stuff inside the switch statement. So let's move all of the contents of the switch statement into that as well. So we're going to put it into here, and we need to tab it in a bit as well. So this is what we've done. I think this is what we're going to do here. So we've got this if 10 milliseconds, so I have to, okay, I've got to put another label here. I'm starting to lose track of all my curly brackets. So this is the if 10 milliseconds flag is equal to 1. We go down to here, oops, this one, and we find the matching bracket. Okay, it's already there. What's the matching bracket for this guy? I want to label this. As you can see, I'm already starting, okay, this is it. I'm already starting to lose track of my brackets. And this is actually very simple software. There's really not much to this. So you can see why I'm doing this kind of thing. There. All right. So, I think this is how it's going to work. So what we're doing here in this while statement, most of the time we're doing nothing, except we're testing that flag. We're just testing this 10 millisecond flag. And so if the flag is not equal to 1, all we're going to do is go down to the bottom here, and then we're going to hit the bottom of the while statement, and we're going to go back up and back into the while statement again, and we're just going to continue looping through many times for 10 milliseconds until this flag gets set. When the flag is set, that means we've elapsed 10 milliseconds. The counter has already done its thing, it's reset and ready, and it's starting over again. That's why I chose the mode that I did. So I don't have to intervene with the timer, I just let the timer do its own thing. There is another way. I could have written the timer counter register with this value, but every time it interrupted, I'd have to rewrite that value into the register. So that the way I did it makes it a lot simpler. So anyways, 10 milliseconds elapsed, the flag is set, we clear the flag, and now we got to count that delay. So we don't want to do this every 10 milliseconds, so we got to wait a number of 10 millisecond timeouts. So we simply decrement our LED delay and check to see if it's equal to 0. If it's not 0, we are not going to do anything. So we're going to hit there's the other end of the if statement here. We hit the end of the first if statement, the end of the while, and we go back to the while again, and we sit there humming away on the 10 millisecond flag. Eventually, our LED delay is going to decrement down to 0. First thing we do is reset it, because we don't want to forget that. It's important to reset it or you'll have some screwy results. And the next thing we're going to do is we're going to change the LED state, so we increment it. And just test to see that it hasn't reached the end yet. If it hasn't reached the end, we're not going to do anything here, so this statement won't get executed. If it has reached the end, we're going to reset it to the beginning again. And now our LED state has changed. We're going to hit the switch statement here, and then we're going to execute one of these bits of code only, depending on the state of LED state. And then we're going to go to the end of the switch statement, which hits the end of the if statement, the other end of the if statement, and hits the while statement, and goes back, and then we're back sitting here looking at the 10 millisecond flag. Now, this looks really complicated. Once you get used to doing this and you wrap your head around it, you will understand it much better. But this is the way you have to do it. Now, I could have in here a bunch more statements of another process going on, and the microcontroller can execute all that stuff as long as that other state or whatever it does is not long, doesn't take longer than 10 milliseconds. You can do a whole lot in 10 milliseconds. 10 milliseconds is a long time for this this microcontroller, even running at 8 megahertz. At 16 megahertz, it can do a whole lot of instructions. And so you can have more code in here doing other things that the microcontroller be doing while it's waiting for the 10 millisecond flag to get set. And then it can finish that, and if it's less than 10 milliseconds, it'll just sit there and wait for the 10 millisecond flag and then go on and do something else. So you can set up different timers here as well. And so LED delay is one of the timers. I could create another timer for another process and do the same thing again using a switch statement or whatever that's needed to be done. So that is essentially it for the software for this. What I'm going to do is I'll put it up on my GitHub site. You can have a look at it, you can download it and play with it. Well, actually, I should probably compile it and see if it actually works. Let's first of all just see if I don't get any mistakes or any errors in the compiler. Uh-oh. What did I get here? I think I may have written my ISR something wrong here. I'm not sure why it did this. I'm going to have to go offline here and figure out what I've done wrong. So I'll see you in a few minutes here. Okay, back again. I forgot to include the library for the interrupts, and that's why it gave me an error. When I compile it after put this include statement in here, it compiled with any problems. So the next thing I'm going to do is burn it into the microcontroller and see if it actually works. Okay, back again in the code. So yeah, when I compiled it and burned it into the microcontroller, it didn't work. And I spent a bit of time checking out, and I made a couple of very simple blunders, but they're obvious once you figure them out. First of all, I forgot to set the interrupt, the global interrupt enable flag, and so there was no interrupts occurring. It still didn't work when I did that, and I realized again I made a very fundamental error. The timer 10 millisecond flag gets checked here, but you have to define it in a special way because it's checked here, but it gets set somewhere else. But the compiler will automatically optimize out the flag here. So basically, the flag was never really being tested, and so nothing would happen. It just sits in this loop here, doing nothing, just testing nothing. And so what you have to do, and this is a rule that you should remember, any variable that gets changed by an interrupt, you need to make that variable volatile. And that tells the compiler that this flag gets used, or this variable gets used in many different places in the software, and it has to be handled a little bit differently. And once I did that, it worked just fine. So this is the code showing you how to use a timer to create the timing for your processes. I could show you the blinking LEDs. It looks exactly the same as before. They all blink on for about a half a second. I think I used 500 milliseconds in the previous one. And so it doesn't look any different. It's just the way it operates. And unfortunately, to do this where you're using your microcontroller most efficiently, you have to do a much more complicated code with this state machine. But I hope that you can understand how state machines work and how to implement them. At least this is my way of implementing these state machines. Probably not the only way to do it. I haven't seen anybody else do it any differently, but I'm sure there must be some better ways perhaps than what I do. But this way works, and it's actually pretty straightforward and simple to use. So that's about it here. We went through setting up timer 0 to create an interrupt at a known interval. Now again, because of the speed of the microcontroller's crystal oscillator, we had to massage timer 0 a little bit to get the longer delays that we wanted, but it wasn't very hard to do. We created an additional counter here, LED delay, and used that to extend the 10 millisecond counts. So if we wanted to do other delays here of different values, we could do that with different timers other than LED delay. And the only thing is our granularity, like how our resolution of our timer is no better than 10 milliseconds. So we can only change our timer count or a delay by increments of 10 milliseconds. What else did we do here? We set up a state machine using the switch statement, and that's about it. Some of the programming shortcuts that I did here, the post decrement and pre-increment of a variable. I could put the decrement sign in front of this, which means it would decrement first and then check for 0, which is not what we wanted, because 0 is a valid state here. So what I did here is I had it check for 0 first, and then if it was not 0, then it would decrement it. And then over here, what I did was I increment it first, and then I checked to see if it reached the maximum LED state. I could have done it the same way here with the decrement or the increment after, and I could just have checked for LED state 6 instead of max LED state. Either way works. It doesn't really matter how you do it as long as you get what you want. And here you have to, of course, reset LED state to the beginning again. So that's about it for this video. I think in my next video I might do something again with an LED, but I'm going to use a PWM using timer 0 again, but I'll set it up to make it into a PWM so we can vary the intensity of an LED. So that's it for this video. Hope you enjoyed it. Stay tuned for the next one. Do check out the code on my GitHub site. There'll be a link down below the video here for that for this code. I probably will massage this code a bit and add some comments just to make it a little more easy to understand what's going on. It'll be a little bit different than what you see here, but this code will be available freely available to download and play with as you wish. Thanks for watching.